All right, let's go ahead and do this. So separating something like this might look kind of terrible first, but it's actually not that bad. On the right-hand side, I don't have any t's. So I'm going to bring essentially everything on the right-hand side over to the left. Now, there's a couple different ways to do this, and I'm going to try and make it nice, but I'll show you kind of the less nice way first. If I was going to separate this and wasn't trying to be super kind of specific about it, I might just say, well, I'm going to multiply the whole thing by dt. So I'm going to get ds equal to all of that times dt. And then you could literally just divide by all this so that you have 1 over 8 minus s over 25 equal ds equal to dt, which is fine. But there's a way to make this a little bit nicer. I would rather not have s over 25 in my denominator. So I might multiply this left-hand side by 25 over 25. Actually, I'd probably multiply both sides by 1 over 25 if I was really being perfectly honest. So I would probably rewrite this as 1 over 25 times 1 over 8 minus s over 25 ds equal to 1 over 25 times dt. We're just doing the same differential equation we ended last class with, but we're doing it using separation of variables now. So now for this left-hand side here, if I distribute the 25 times 8 always seems challenging until you remember that 25 times 4 is 100. So 25 times 8 is just 25 times 4 times 2, which is 200. And then 25 times s over 25 is just going to be s. So we end up with 1 over 200 minus s ds equal to 1 over 25 dt. And that is not too terrible to anti-differentiate on both sides. So let's see what we get. It's easy to miss a small little detail integrating the left-hand side here. It's really, really easy to think the left-hand side is going to be just the natural log of the absolute value of 200 minus s. But it's not quite that. So if we differentiate that, you get 1 over your stuff times the derivative of your stuff, which is a -1. So we, oh yeah, question. Did I forget to do something here? I thought I multiplied 25 by everything. So I multiplied the top, or so I multiplied both sides by 1 over 25. So 25 times 8 gave me 200. 25 times s over 25 gave me s. Yeah, I think we're good. So what I'm saying over here is that we definitely, this isn't quite right because if you take the derivative of it, you get natural log, or you get 1 over 200 minus s times -1, and I don't have a -1 there, so I need a -1 to account for that. So the antiderivative of 1 over 200 minus s is negative natural log of the absolute value of 200 minus s. Antiderivative of a constant is just the constant times the variable plus c. I'm trying to remember, actually. Let me take a look. Does this look like we have that one? Good question. I'm curious. No, it looks very different than where we started. So this process is the process is gonna look quite different than the first order linear differential equation process where you multiply both sides or where you use the integrating factor. So solving this, I'm going to try and isolate the function s. So multiply both sides by -1. So the natural log of the absolute value of 200 minus s equals -1 over 25 times t. -1 times a constant is still a constant. So I'm still going to write plus c, even though I could have just as easily written minus c. We don't. Why? I don't know, because someone just wants to be difficult. And then we're trying to solve for s here. So exponentiate both sides. The absolute value of 200 minus s is equal to e to the -1 over 25 times t plus c. Usually I would have dropped the absolute values by now, but I'm going to show the work that I saw. At least I saw this in Lee's notes for sure, where he is showing all the steps where you get to the point where you get to drop them. So let me just point that out. I think you really have been here just said natural log of 200 minus s and not where you got the absolute values. But here's the work someone might want you to show to justify that. Rewrite the right-hand side here as e to the -1 over 25t times e to the c. And then we're going to say that not the absolute value, the 200 minus S is equal to plus or minus e to the c times e to the negative 1 over 25t. And then you're going to call that some new constant. That's how you get to justify that. So I'm going to say that 200 minus S is equal to A times, I should really be writing this as e to the negative t over 25. Let's make our lives a little bit less terrible. And we're almost done. We're going to solve for S. So I'm going to subtract the A e to the negative t over 25 to the left and add the S to the right. So I'm going to get 200 minus A e to the negative t over 25 equal to S of t. That's our general solution. And now let me remind you from the problem that we did at the end of last class, we also had an initial condition. Our initial condition was that the tank had 10 pounds of salt at time equal to 0. So if I plug in t equal to 0 and set S equal to 10, I get 200 minus A times e to the 0 equal to 10. So that A ends up having to equal 190. So then our actual solution is that S of t equals 200 minus 190 times e to the negative t over 25. And the reason I'm showing you this is because I want you to see that sometimes there are certain differential equations where you could either use first order linear differential integrating factor, or you can do separation of variables. There's not a lot of them. They kind of are very specific how they look, but I just want to show you back from the notes from last class, just so you can really believe it. If you want to look yourself, here's the solution we found last time, which was S of t equal to 200 minus 190. I wrote it differently there, but that's the same as times e to the negative t over 25. So really doing it either way yields the same solution, which is good because it should. You shouldn't get a different solution to a different equation just because you tried to solve it a different way. Cool. What else to say about this? We could ask a couple questions. So sometimes after you've solved a differential equation, someone wants to ask you like, maybe what happens after 25 minutes, or what happens after some amount of time, or how long is it until you get to some certain amount of salt. So those are pretty, I don't want to say they're standard, but they're easy questions to ask. I could very much say, okay, maybe I could ask the question like, how much salt will be in the tank if we do this for, I don't know, 2.5 hours? Well, that's the easier type of question. The way we answer that question is just by setting t equal to the appropriate value and plugging it in. Now, we do have to note that t isn't measured in hours, t is measured in minutes. So we need to plug in t in minutes. So 2.5 hours, so 2.5 hours times 60 minutes is going to give me 150 minutes. So we're trying to find S of 150. That's going to be 200 minus 190 times e to the negative 150 over 25. And honestly, I would probably just leave my answer like that. I would leave my answer like that unless someone asked me like, actually, like what, like how much, like to me, that's not very meaningful. Like I don't actually know how much that is. That could be a lot of salt, that could be not a lot of salt. So if I actually want to know what that is, I kind of need to plug it into a calculator to see what I get. So let's do a little bit of simplifying here. 150 divided by 25 is just 6, right? Because there's 6 25s and 150. So that really becomes 200 minus 190 e to the negative 6. And then I need a calculator. So I get my calculator out. Can you even see what's on my calculator? Well, you kind of can. If I move it over a little bit, that's worse. Over there, no, that's worse. Maybe you can kind of see that. I don't know. Not really. Anyway, e to the negative 6 is not too terrible. So we do e to, oops, that's not e. We do e to the negative 6. We get something really, really small, like 0.002. we multiply that by 190, and then we subtract 200 minus it. So after 2.5 hours, you're pretty much close to the limit of how much salt you can get, right? There's not much more salt you can get than 200 pounds of salt in this tank, because this is just going to get smaller and smaller and smaller, but it's never going to go to zero. So after 150 minutes, we're getting 199.53 pounds of salt. There's really not any more you can get. The other type of question people often like to ask is, let's not get too twisted over here, is how long does it take to get to a certain amount of salt? So the other question we could ask is, how long until the tank has 100 pounds of salt? And this question involves doing the opposite kind of thing, right? We're going to take our equation and set it equal to 100 pounds instead of setting time equal to something. So we're going to take our equation, which is right. I don't actually have it without the t there. It's going to be S of t, which was 200 minus 190 e to the negative t over 25, and set that equal to 100. And then do the algebra to solve it. So if it were me, I would subtract 200. So I've got negative 190 e to the negative t over 25. 100 minus 200 is negative 100. Divide by 190, so you've got e to the negative t over 25 equal to, instead of saying 100 over 190, let's write 10 over 19. Take the natural log of both sides. So that negative t over 25 equals the natural log of 10 over 19. And then multiply both sides by negative 25. So t is equal to negative 25 times the natural log of 10 over 19. Am I getting a negative time? That doesn't seem right. We aren't getting a negative time. But the thing is, this can look confusing if you're not super careful. Natural log of 10 over 19 is a negative number. If you think about the graph of the natural log, it's negative if your input is less than 1, which this certainly is. So this is positive, so we're okay. Also, you could check with the calculator, right? You could actually find the natural log of 10 divided by 19, which is that. So here's a math mistake. Look at what I did. I did the natural log of 10 divided by 19. And I know it's a mistake because I got a positive number. Because what did I do? I didn't use parentheses. What I actually calculated there was the natural log of 10, and then I divided that answer by 19. I should be more careful. I should have written the natural log of 10 divided by 19 in parentheses. And now I should get a negative answer. Negative 0.64. Wildly different number. So be careful when you're using a calculator. If you're using a calculator, right? It's easy to make mistakes like that if you're not paying attention. And I'm going to multiply that by negative 25 to get 16 minutes approximately. So approximately 16 minutes. Again, I wouldn't usually give a decimal answer, but if someone's actually asking how much time something took, telling them it was a negative 25 natural log of 10/19 minutes, although exact, doesn't really tell them what it is. So that's why I like to kind of give a decimal approximation in those situations. Okay, so let's go that way. We're still, everyone's still in chapter 7, right? We haven't gotten to chapter 8, which is talking about like the matrix stuff and all that jazz. We're almost on the precipice of getting to that, but we still got a little bit more to go. So let's do a few more examples. Oh yeah, let's especially do that. Sorry, I'm trying to keep everything in order. I've got a jillion papers all over the place because that's just how I roll. Let's look at this example. Sure. Yeah. And as always, if I'm off frame, tell me, please. Sometimes, things are out of place. I'm happy to adjust. It's right there in front of me. Sometimes I'm not always seeing it. So let's say we've got this situation. Suppose the population of ducks in the Arboretum. By the way, don't feed the ducks. In case no one's ever told you, do not feed the ducks. It's also against California law / policy, but it's also not good for the ducks. So don't feed the ducks. Anyway, that's all I have to say about that. Suppose the population of ducks in the Arboretum is growing according to the differential equation, dn dt equal to 2 times n times 1 minus n over 1,000. Okay, what's the name of this thing that I'm saying here? Yeah, this is the example of like a logistic growth model, which you don't actually see from the differential equation, right? The logistic growth model is more what the actual solution looks like, but this type of differential equation leads to a logistic growth model, which we will talk about. But the idea here, and I actually kind of like to write this a slightly different way. I like to factor out the 1 over 1,000 and write it as dn dt equal to 1 over 1,000 times 2 times n times 1,000 minus n. Either way is totally fine. I like seeing it this way because to me, it's a little bit more clear this way that 1,000 is kind of the limiting factor for the number of ducks you can have. Let me ask you this. If I got to a place where my n was bigger than 1,000, like let's say n was 1,005, if I plugged in 1,005 for n, I'd have a negative number here, I'd have a positive number here, and the rest is positive. So overall, this whole thing would be negative. So I just want to point out that if n is bigger than 1,000, then the rate of change is negative. So if the population gets too big, it gets pushed back to being not quite that big, right? Because if you go over 1,000, you're like, oh, the habitat can't support that many ducks. We're going to grow negatively. On the other hand, if n is bigger than 0 here, but still less than 1,000, like for example, 600. If you plug in 600, 2 times 600 times 400 is definitely a positive number. So if we're in between 0 and 1,000, the rate of change is going to be positive. Meaning if you have between 0 and 1,000 ducks, you're going to increase the number of ducks because the population can still, or the habitat can still support more ducks up until that limiting factor, that limiting amount of 1,000. So you might have already guessed this, but we're going to draw the phase plot and see that 1,000 is going to be a stable equilibrium and the other equilibrium is going to be unstable. But definitely just from the words we've said, right? If you go above 1,000, you're getting pushed back towards it. If you go below 1,000, you're getting pushed up towards it. We can draw it though. So let's draw the phase plot. Draw the phase plot. And I guess to say, before we draw the phase plot, we should find the equilibria. So we're going to set our derivative. And I'm going to write it this way because this is more standard, even though I like this better. Set your derivative 2 times n times 1 minus n over 1,000 equal to 0. We definitely get n equal to 0 as one equilibrium, which makes sense. If you have exactly 0 ducks, the rate of change of ducks is going to be 0. You don't get more ducks if you've got no ducks. Or that's going to be n equal to 1,000. I've got 2 equilibria. This is definitely a second degree polynomial, right? If you actually multiply this all out, you get n squared or some multiple of n squared plus some multiple of n. That's a quadratic. The graph is going to look like a parabola. And we just have to decide if it's upward opening or downward opening. Well, if we actually multiply this out, I don't even want to multiply it out. Let's not do that much work. Instead, we're like, here's n equal to 0. And over here is n equal to 1,000. And I'll remind you all, right, on the horizontal axis, we're graphing, or we're labeling it as n, whatever the population is, or the solution. And on the y-axis is the derivative of that thing. And we already said all the words we needed to say. Between 0 and 1,000, we know that the derivative is positive. So it's going to be something like that. And then bigger than 1,000, the derivative is negative. Less than 0, the derivative would also be negative. If you plug in a number that's negative, although it doesn't really make sense to have negative ducks. If you had negative ducks, you would have more negative. That seems, it's not very good interpretation to have this piece of the graph here. Oh, well. That's life. Sometimes part of the graph doesn't make sense. And in the usual way, like a red pen, please. and really the best way to do this is the way I've never seen a better way of doing this other than the way everyone always does it. Okay. I take that back a little. There is another way of doing it, but the graphical way is the easier way. In here, between 0 and 1,000, is my graph positive or negative? Positive. So that means n is increasing because dn dt is positive. Dn dt being positive means that n is increasing. Over here, to the right of that equilibrium, the derivative is negative. So n is decreasing. So dn dt is less than 0 there. So n is decreasing. Meaning, if you start here, the number n is going to get smaller and smaller and smaller and smaller and smaller. If you start over here, it's going to get bigger and bigger and bigger. And it doesn't really make sense to say it over here, but I'm going to say it anyway. If you started with negative ducks, you get less and less ducks, which again sounds really stupid. So I feel like bad for even saying it, but that's what the graph would be telling us if it made sense. So definitely n equal to 1,000 is a stable equilibrium. Because if you try to be bigger than 1,000 or less than 1,000, you're going to get pushed back towards being equal to 1,000. On the other hand, n equal to 0 is unstable. I forgot a word there. Fine, it's all right. Is an unstable equilibrium. Equilibrium, I can spell. Specifically here, if n is a little bit bigger than 0, you get pushed away from 0. Or if n was smaller than 0, you get pushed away from whatever. So the words we kind of use here are if you have a slight perturbation in your equilibrium, if you're just a little bit off one side or the other, if you get pushed back towards it, you're stable. If you get pushed away from it, you're unstable. That's the whole gist. There's also another way you can show this though, which I might as well point out here. So if we call this, I think G of n is typical notation here. I will point out that for the unstable equilibrium, is the slope of the tangent line positive or negative? Let's see here. It looks pretty positive to me. And for the stable equilibrium, the slope of the tangent line is definitely negative. And that is generally true. If you have a stable equilibrium, its tangent line will have a negative slope. If you have an unstable equilibrium, its tangent line will have a positive slope. So another way to go about doing this, although I don't like it as much as graphing it, because graphing it just feels super easy to me, is to take your differential equation, call it G of n, 2 times n times 1 minus n over 1,000, and take the derivative and see if it's positive or negative at those places. Now, I don't want to use the product rule. That's way too much work. Let's just multiply this out first. So if I distribute the 2n to both parts, I'm going to get 2n minus 2n times n is 2n squared over 1,000. If you really, really felt compelled to, you could simplify this as 2n minus 2 over 1,000 reduces to 1 over 500 times n squared. I don't think you really need to do that, whatever. Okay, so let's find the derivative of that. The derivative is going to equal 2 minus 1 over 500 times 2n. Not a hard derivative to find. Should be a straight up line because we're taking the derivative of a parabola. All right, let's plug in our two equilibrium points and see what happens. So I plug in 0, I get 2 minus 0, which is 2, which is positive, which is unstable. If I plug in 1,000, I get 2 minus 1 over 500 times 2,000. 2,000 over 500 is 4. 2 minus 4 is negative 2, which is negative, which means it is stable. I would say this is a good way of doing it if graphing the differential equation is really hard to do. Like it's hard to make the face pop because maybe the function is just something really weird. This is a good thing to do. This is like the backup method, right? If it were me and I was asked to determine if these equilibria were stable or unstable, and no one gave me any other instruction about how to do it, I would first go towards making the phase plot. graph the thing, see if it's going up to down, or negative to positive or positive to negative, and determine and just draw the little arrows. But if the thing was really hard to draw, or maybe it wasn't really easy to determine the equilibrium, you still have to be able to find the equilibrium. If the thing was hard to draw, if it was just a graph that looked gross, I would probably then jump to this instead, because it's probably going to be easier in some sense. Questions about this before we're not done with this example yet, but are there any questions about what we've done so far? We are going to solve this one, which will be a little bit gross, but it's worth seeing, I think, because I know, at least I'm pretty sure for Lee, I think Lee does usually have you all solve at least a couple of these. So you should look at it. And it's good for everyone else to see it too. How did G prime of n come to be? That is a G prime. So the way G prime, so we made up G of n, right? We said, we're just going to call whatever dn dt is equal to, that's what we're calling G of n. And so instead of using the product rule, although I totally could, right? We could use the product rule if we really wanted to. I could have said G prime of n is derivative of 2n times 1 minus n over 1,000 plus 2n times the derivative of this is going to be 0 minus 1 over 1,000. I could have taken the derivative that way, but I would prefer to not use the product rule when it's easy to multiply the thing out. So I just distributed the 2n to each of those terms. 2n times 1 is 2n. 2n times minus n over 1,000 is 2 times n squared over 1,000, or should be minus 2 times n squared over 1,000, which reduces to 1 over 500 times n squared. And then I took the derivative of that. The derivative of 2n is just 2. The derivative of n squared is just 2n, and that constant just hangs out. So that's how we found G prime. The other thing people sometimes do is they ask you to graph what the what do you call it? The solution curves look like. So sometimes people ask you to graph or sketch. Let's see if that was sufficient here. Thank you. Yeah. Yes. The solution curves, meaning we are graphing time on the horizontal axis and n of t on the vertical axis. And this is where it's really important to know what the equilibria are. So the equilibria was n equal to 1,000, the stable one anyway. So let's draw that up here. So there's n equal to 1,000. And just like the other one, if n starts below 1,000, it's going to get pushed towards 1,000. If n starts above 1,000, it's going to get pushed towards 1,000. Yeah, and that's, well, I'll say a little bit more. So we start up here at 1,500. That's way too many ducks. There's not enough habitat, so it's going to end up going down like that. And the same is true if we start down here. It's going to go up like that. Even if we start way down here with just a couple ducks, basically your stable equilibrium value is your horizontal asymptote, because things get pushed towards it. If you have more than one, then other things happen. And I will point out, if it made sense to start with a negative value of ducks, you would get pushed further and further away from your unstable equilibrium of 0. But again, at least in the context of ducks, that doesn't really make a lot of sense. Yeah. That's a question that's not easy to answer, because we don't. So semi-stable would mean graphically, right? You had something that bounced off your axis, right? So you came. In fact, let me grab this for you. So a graph that's semi-stable, right? You maybe look something like you've got and you're doing something like this, and then maybe something like that. And let's just make up some numbers. So let's say, there's 0 again. Let's say this is 500. Let's say this is 2,000. So here, 500 is semi-stable, I think, right? Because if we're less than 500, our derivative is positive, so we're getting pushed towards it. Again, right? This is n of t, this is dn dt. But if we're bigger than 500, then we're getting pushed away from it. And if we're bigger than 2,000, we're getting pushed back towards it. So I'm not super great at interpreting these things. Like at least I'm not super great at interpreting semi-stability because it's something that's really hard to say. Kind of like I know that 2000 is a stable equilibrium. Like if you have less than 2000 ducks or more than 2000 ducks, you're getting pushed towards that number. I guess you could say here, if you have less than 500, you might end up getting pushed towards 500. And if you're able to kind of like guarantee that you stopped right at 500, then you would stay there. But the thing about a semi-stable thing, and you'll see this is also kind of the analog of this when you take 17C is when you talk about saddles in your stability situation here, is that it's a very unstable stability, right? If you go off of it just a little bit on one side, you're going to get pushed way away from it. So you're stable like in that one instance, but it's a very fine balancing act. But I don't have a good like physical word interpretation of what that really means as far as like a population of animals. It might not really make sense in that context. So be a good question for your professor. They might not have a good answer either, though, to be perfectly honest. Hopefully that was enough of some sort of answer to say word at least. So let's go ahead and talk about how you would actually solve this differential equation. It is a little bit gross, I won't lie, but it's not super terrible. So let's start off with dn dt equal to 2 times n times, what was it, 1 minus n over 1,000? I believe that's correct, yeah. And now we're going to solve it. I will point out it is definitely not first order. Because if you multiply out the right-hand side, what power of n do you get? What's the highest power of n you get? I should use more words there, sorry. I should have said it's not first order linear. It is definitely first order. Right, it's a first order differential equation because we only have the first derivative. But it's not linear because the solution we're looking for, or the function that is our solution, we have a second degree power of that. So it's quadratic. You could say this is a first order quadratic differential equation, which we don't have any particular method of solving. So we know it's not first order linear. The only other option is it must be start to the S. I want you all to say it. So we have two kinds of differential equations we're able to solve. One of them uses mu, where we do the whole mu thing, and the other kind we've been solving are the ones that are separable. It's a separable differential equation, which means we should be able to bring all of the one things to the left and the other things to the right. So I need to bring all the n's to the left. So I'm going to say I've got this n and this n dividing over, so I have 1 over n times 1 minus n over 1,000 equal to, oh, sorry, don't forget the dn equal to 2 times dt. People do this in different ways. I, again, would prefer not to have an n over 1,000 here. Just like how in the first example we did today, I didn't want to have t over 20 or s over 25 in my denominator. So I'm going to multiply. You could either multiply by 1,000 over 1,000, which might be the way to go here, or you can multiply both sides by 1 over 1,000. There's not one better way. You can take your pick. Let's do 1,000 over 1,000 here just to do it differently than we did last time. So 1,000 over 1,000. So I'm going to be having 1,000 times 1. And I'm multiplying the 1,000 specifically by this second factor here, right? We're not distributing. When you have stuff times stuff times stuff, you just multiply any two together first. I'm multiplying this one by that one first. 1,000 times 1 minus n over 1,000 is going to give me 1,000 minus n. And then we're going to integrate both sides. And oh, look, the left-hand side is a factor denominator, which means we're probably going to use partial fractions. This kind of differential equation always results in having to use partial fractions. There's no other way to do it. So we're going to do the partial fraction decomposition. So we have off on the left here, 1,000 over n times 1,000 minus n equal to a over n plus b over 1,000 minus n. Someday I'll be able to write a b that doesn't look like a 13, but it's not today, clearly. Multiply both sides by the common denominator. So you're going to get 1,000 on the left equal to a times 1,000 minus n. minus n plus b times n. Do the smart thing, pick the convenient values. Pick n equal to 0 and get 1,000 equal to a times 1,000. So a is going to equal 1. How nice. And pick n equal to 1,000. So then 1,000 is equal to a times 0 plus b times 1,000. Oh, b is also 1. How nice. I will point out, even though I didn't intend it, I certainly made the better choice here by leaving the 1,000 up here versus bringing it down there. My coefficients ended up being much nicer this way. Could we have fixed it later on? Sure, but it happened to turn out nicely this way. If I had had the 1 over 1,000 down there and I ended up with like 1 over 1,000 or 1 over 1,000 over some stuff, I probably would have multiplied it back over. So now we can rewrite the left-hand side as the integral of 1 over n plus 1 over 1,000 minus n. I suppose I could integrate this right-hand side here. The integral of 2 dt is 2t plus a constant. All right, there's so many logarithms, right? It's all like most of these problems, you're getting logarithms most of the time. Not always every time, but a lot of the time. Integral of 1 over n is going to be the natural log of the absolute value of n. The integral of 1 over 1,000 minus n is going to be the natural log of the absolute value of 1,000 minus n times -1. Just like the previous one we did where there was a 1 over something minus the variable. So it's going to be minus the natural log of the absolute value of 1,000 minus n. Solving the rest of this is just gross algebra. But at least from my experience, it is algebra that Lee expects people to do or has in the past. Maybe he's changed his mind. I don't know. So here are the steps to solve this. All right, let's get ourselves a new piece of paper because it gets a little bit gross. So I want to solve for n. And in the end, we'll throw in, actually, let's throw in right now. Sorry, that looks kind of terrible. Equal to 2t plus c. And also, let's give ourselves an initial condition just so we can actually practice solving for that as well. So let's say that our initial condition is that, let's say at time equal to 0, we have 300 ducks. Just so we can practice picking the right moment to solve for c, which I will tell you, I don't know what it is. I'm going to be guessing here, which is fine. That's how a lot of math works. You guess, and maybe you turned out to make a good guess. Maybe you didn't. A lot of integration is just guessing, like guessing what method to use. The first step here, though, is to combine these two logarithms. You want to write this as the natural log of the absolute value of n over 1,000 minus n equal to 2t plus c. And then do the usual thing. Exponentiate both sides. Let's give ourselves some more room to work with here. E to the natural log of all that stuff equals e to the 2t plus c. I feel like you've seen this enough times to know that e to the 2t plus c is going to be e to the c times e to the 2t, and then we're going to say that it's a plus or minus e to the c, and that's it. So I'm going to say that I have the absolute value of n over 1,000 minus n equal to e to the c times e to the 2t. And then the n over 1,000 minus n gets to be my plus or minus e to the c, which I'm just going to call a. But just so everyone knows, right, that a is either positive or negative e to the c. I personally don't love the way most people solve this from here out. Most people do this thing where they flip both sides over. It's fine. It works. It's not what I like to do, but it is. I'll show it to you though, because it is what people do. So one way of doing this is just to reciprocate both sides. So 1,000 minus n divided by n equals 1 over a e to the 2t. I really don't like it. I really just so not a fan. And then I don't know why you even do that. I don't know. I can't make it work in my brain that way. I still just want to cross multiply. So what I would do is not this. It's not the way James does it. It's fine. Not everybody has to do it the same way. I would just multiply both sides by 1,000 minus n. Ooh, did I miss my moment? Was that the moment I should have solved for A? Maybe. Is it going to be better here to solve for A? I think it's best here, right? Right there is where I have A kind of as isolated as it's going to get. So I think here is actually the moment where we should have said, let's plug in and figure out what A is. So if N is 300, I get 300 over 1,000 minus 300 equal to A times E to the 0. That's just 1. So 3/7 is my A value. I feel like that's the time. I could be wrong. There might be a better moment, but it's not terrible. So now I've got N equal to 3/7 e to the 2t times 1,000 minus N. I still have to solve for N. So I have to distribute this here. So N equals 3/7 e to the 2t times 1,000 minus 3/7 e to the 2t times N. Add that over here. So now you've got N plus 3/7 e to the 2t times N. 3 times 1,000 is 3,000. So let's say we got 3,007 e to the 2t. Factor out the N. And divide by what's left over. So N as a function of time is equal to 3,007 e to the 2t divided by 1 plus 3/7 e to the 2t. And I would definitely make the choice to get rid of those sevens, multiply the top and bottom by 7, which is pretty standard, I think. So rewriting this in the nicest way possible, in my opinion, we're going to get 3,000. 3,000 seems awfully big. E to the 2t over 7 plus 3 e to the 2t. That's how I would choose to write it. Other people might pick something different. Let me actually, other people probably would pick something different. Other people would probably divide everything by e to the 2t and write it as, and there is a good reason for what I'm about to do. It's not just because other people would do it, it's because it actually probably shows something more important better. Everyone would probably say, I've got 3,000 over 7 over e to the 2t plus 3. Because then it's a little more clear that as t goes to infinity, this part right here is going to go to 0. Because you've got 7 divided by something that's getting infinitely large. And then you're going to get 3,000 over 0 plus 3, which is 1,000, which it should be because 1,000 was the stable equilibrium. So no matter what you start at, if you let time go to infinity and you've only got one stable equilibrium, you should be getting closer and closer to that stable equilibrium. Let me clarify that slightly. If you started at a place where you would end up being, like if we started with a negative number of ducks, we would have gone way off to negative infinity land, but we didn't. Yeah. So when you solve these, it's a little gross. I would probably rewrite it as, I rewrite it like 20 times, and that's probably my final opinion on the matter. There is how someone would write it. Any of the ways I've written it are correct. You just might see your professor write it a different way. So I don't want to be like, oh, he wrote it that way and I wrote it that way, and they look totally different. No, they're not that different. They are the same, but you have to be able to see that one is the same as the other. All right. It's Friday. It's 2:56 p.m. I say we can call it a day.